Welcome to AI driven perception, learning and mapping for drones. Lecture 4. We talk about foundations in neural network. Here we introduce Perceptron. Let's look at the learning objective of this particular lecture. We talk about mathematical representation of the perceptron. We can talk about learning Boolean logic using perceptron. Then we talk about problem of separability, we call linear separability. And we talk about example with a linear activation function and sigmoidal activation function. And we talk about linear inseparability, solving multi-class classification using multiple perceptron problem. Right? What's perceptron? You remember the single neuron model we introduced in the last time receives the input signal x1, x2, xm from dendrites and passing through the synaptic weight, right, and also having a bias x0, w0, which results in summation j is equal to 0 to m wj xj. This is our activation potential passing through an activation function and gives an output y. Here w0 is a programmable bias and x0 equal to 1. Mathematically, if you have to represent, y is g, this is activation function g, w0 x0 plus summation j is equal to 1 to m wj xj. Right? If I want to represent them in a matrix vector term, y is nothing but g w transpose x. Here the w is a vector, m plus 1 dimensional vector, x is a m plus 1 dimensional vector. Okay. Let us look at perceptron with the discrete activation function. Okay. We are looking at a neuron model with a unipolar hard limit activation function and see whether we can use this hard limit activation function to represent AND gate, which is a 2 input, right, and we are considering the bias weight w0 to be 1.5. What are the inputs? x1 and x2 are the input. If you look at the AND gate, 0 0 it will give 0, 0 1 it will give 0, 1 0 it will give 0, 1 1 it is 1. We are introducing a bias x0 which is 1 1 1, bias value being 1. Now let us look at the architecture. There are 3 inputs, 2 signals are coming from dendrites. There is one bias signal and these are my weights. The W1 and W2, the weights are same, which is equal to 1, whereas the W0 weight is minus 1.5. We have 4 samples, sample 1, sample 2, second row is sample 2, sample 3 and sample 4. Let us take a first sample, which is the first row, minus 1.5, 0, 0. Sorry, there is an error here, it is 1 0 0, right. So what we are doing is g is equal to the weight minus 1.5 into 1, 0 into 1, 0 into 1 results in activation potential of minus 1.5, which is less than 0. So the output is 0, which is matching. Let us say we look at 1 0 1. 1 into minus 1.5 is minus 1.5, 0 into 1 is 0, 1 into 1 is 1. So minus 1.5 plus 1, which will be minus 0.5, still negative, it will give us a 0. If you look at the third row, 1 1 0, that will also give the negative value of minus 0.5, so output is 0. If you look at the fourth row, right, minus 1.5 plus 1 plus 1, which will give plus 0.5. Plus 0.5 means it is what we are using unipolar activation function, which will give output greater than 0, which means 1, right. So you can represent a Boolean gate using a simple perceptron, right. That is our advantage. If I am trying to represent the activation function, let us look at it. All zeros belongs to class red color. If this output is 1, it belongs to class 1, which is represented by x mark, right. So this is my data point in a 2-dimensional plane, right. What we got is a decision boundary x1 plus x2 should equal to 1.5. That is my line which is passing through this, right. So, if you look at it, anything more above this line belongs to class 1, anything below this line belongs to class 0. So, if you see, there are infinite possible solutions are there. You can have multiple lines passing in between, right. If you see, I can draw many lines. I can draw many decision boundaries. I can draw a decision boundary like this, I can draw a decision boundary like this. All these decision boundaries can segregate this class. Okay. Now, let us look at OR gate problem. There are two input and bias, right. What are the input? 0 0 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 1, the bias values are 1, right. Now, this is my weight. Both inputs x1 and x2, the bias is synaptic weight is equal to 1, W naught is minus 0.5. Let us look at the first sample 1 0 0. When x1 and x2 are 0, you have 1 in x naught, so minus 0.5, anything less than 0 is 0, that is your output. If you look at the second row 1 0 1, 1 x naught is 1, so which means minus 0.5, x1 is 0, so 1 into 0 is 0, x2 is 1, 1 into 1 is 1, 1 minus 0.5 which is plus 0.5, anything greater than 0 is 1, so output is 1. So, if I am representing the data in a two-dimensional plane, right, 0 is a class 0 which is represented by dot, whereas the others are represented by the cross ones. You see, this is my decision boundary, right. My decision boundary is x1 plus x2 plus 0.5. As I said earlier, there are infinite solutions are possible. I can have many lines passing through this can give same answers. For every line you will have a different weights, and that is what we are representing as a weight. And if you look at this is a line y is equal to m1 x1 plus m2 x2 plus b. This b is nothing but w naught. This m1 is nothing but w1. m2 is nothing but w2. You can find the equations of line and you can find out these weights very easily. Now, let us see, can I use the same perceptron to identify a NOT gate as a single input, right. x1 0 means the output is 1, 1 means output is 0. I introduce a bias value, the bias values are 1, right. Let us look at the architecture. There are two inputs, one is external signal and the other one is a bias signal, and the weights are 0.5 and minus 1 here, right. Let us look at 1 and 0. 1 into 0.5, that is what we are doing, right. 1 into 0.5 plus 1 into minus 1. So, if you look at it, this will be minus 0.5. So, this will give 0. Whereas, if you look at 1 into 0.5 plus 0 into minus 1 will give 0.5. So, the output is 1. So, I can represent easily the NOT gate. So, if I am just looking at a two-dimensional plane, this is class 0, x marks is represent the class 1, and this is the line which we are talking of. This is x1 plus 0.5 equal to 0. It is a line. If you look at, I can draw many decision boundaries. So many lines can separate these classes, right. So, based on the line equations, you can just find out the weights and represent. Now, let us understand this decision boundary in details. Let us assume a linear activation function, okay. Neuron model with bipolar hard limiting activation, right. G is equal to W naught x naught plus summation j is equal to 1 to m wj xj, and this is my data. I am talking about activation function separating these two data, right. This is my decision boundary, the boundary which separates m dimensional data into two categories, right. I am just representing for this particular problem, right. What is my decision boundary? W1x1 plus W2x2 plus W0x0 equal to 0. That is my decision boundary that we are representing here, right. Let us get a geometric understanding of this decision boundary, right. So, if you look at our equation, summation j is equal to 1 to m wjxj plus w0x0, this if it is greater than 0 for y is equal to 1. Let us assume, just for the sake of argument, the input x we usually take its 1, I am just taking as a minus 1. So that it looks in mathematically we can represent it better. W transpose x should be greater than W0, which what will happen here? W0 x0 will become minus W0, right. So, this one is nothing but W transpose x. So, I can write W transpose x is greater than W0. W transpose x is nothing but norm of weight vector W to norm of x input into cos theta, which should be greater than W0. If I define D is x cos theta, the D is nothing but W0 by norm of W. So, let us understand what is the effect of weights is going to have. If you say this is my decision boundary and this is what I am representing as a D, right, the weights tilt the decision boundary however you want, right. The bias signal, the W0 what we are talking of, position the decision boundary from the origin. If you want to tilt the decision boundary, then I need to use my weights. If I want to shift the decision boundary, then I need to use my bias, if you are geometrically trying to understand. So, weights orient the decision boundary, whereas the bias trying to shift the decision boundary from the origin. So, let us look at different problems, what we call linearly separable problem. There is a data set which is linearly separable. If you can draw a straight line or hyperplane in a higher dimension that can perfectly separate the data point into different category or classes without any misclassification, then we can say it is perfect, linearly separable, right. So, for example, here 2-dimensional plane, for better understanding we are using 2 dimension. All the dark circle belongs to one class, all the purple circle belongs to other class, and I can draw a line, right, which can separate these two classes. Not just one line, there is many lines we can draw which can separate it. Okay. So, this is linearly separable. Okay. If I have few samples purple here, whatever the way you draw the line, you cannot separate. If you look at this blue line, if I call this is my decision boundary, you see these two are misclassified, right, and this is not linearly separable problem. So, if you look at it, the Boolean gates whatever we have used, linearly separable and or not are linearly separable. You can see I can always draw a straight line which can separate them into two groups. It is a 2-dimensional plane, it is a line. For the m-dimensional plane you have hyperplane which can separate the classes into two different categories. Now, let us look at a simple 2-class problem, right, and see whether it can linearly separate. What is my objective? Can I find the decision boundary which can separate these classes, right. So, what is that? Equations of line W0 x0 plus W1 summation j is equal to 1 to m wj xj. If it is greater than 0, it belongs to class 1. If it is less than 0, it belongs to less than or equal to 0, it belongs to class 2, because the way that we are using our activation function, right. Correct classification means I don't want any change in weight. My weights are perfect, the data samples is given, the classification is correct, I don't want change in weight. Otherwise, I need to change the weight. How do we change the weight? That is what we are going to discuss now. Let us say class 1 sample is getting misclassified, right. The weight should change in the direction of the x plane. Let us say this is a sample x, it belongs to class 1, whereas my weight is here, right. So, by looking at it, this is my decision boundary, which means I am misclassifying this into this. So, I need to shift my weight vector in this direction, right, towards the x. So, new weight vector will be like this, right. So, decision boundary started tilting in that direction. So, this is x plus w, assuming the learning rate is equal to 1, right. Let us say if there is a sample which is misclassified into class 2, which belongs to class 1, then weight will be tilted in the opposite direction such that you can handle the classification. So, which means w is w minus eta times x, right. I am here, if you see, my w is here, my x is here, misclassification comes into picture. I am tilting my w in the opposite direction so that the decision surface tilts to capture the relationship. Okay. So, in general rule, the update weight equal to w plus eta e into x. What is e? E is nothing but the error. Error is d minus y. So, d is, let us say 1, y is 1, then error is 0, there is no change in weight. The prediction and the actual labels are same, there is no change in weight. If d is 1, whereas you are talking about y is minus 1, right, then there is a misclassification, right. So, it will tilt like y plus x, where d is 1 minus 1, but y is 1, then tilt like a misclassification in class 2, right. So, if you look at this rule, the way the error tilts and shift to capture the decision boundary, right. If the w naught changes, which will control the shift, whereas the w changes which control the tilt. By tilting and shifting, I will be able to find the decision surface to segregate this data into two groups. Let us look at example so that we can understand better. I am going to use 3 samples, sample 1, sample 2, sample 3. Each sample has 3 dimension, right. So, x1, x2, x3, there are 3 input vectors, right. That is why I have selected a perceptron, the 3 input, 1 programmable bias, whereas w naught is a programmable bias term, here x naught I am assuming to be minus 1. I have a ground truth. The ground truth says sample 1 belongs to class 2, sample 2 and 3 belongs to sample 2 belongs to class 2, sample 3 belongs to class 1. So, I am expecting the label to be minus 1, and 1. I am selecting an activation function, right. It is bipolar activation function, x is greater than 0, it is 1, x is less than 0, it is minus 1, right. I am initializing these weights, there are 4 weights, w1, w2, w3 and w naught, the bias also, right. I am initializing them randomly like this. I am assuming the bias input to be minus 1 here. Let us look at the first sample. First sample 1, minus 1, 0.5 and to x, if I am just looking at it, this activation potential, if you look at it, it is nothing but 1 into minus 1, which is minus 1, minus 1 into 1, which is also minus 1, 0 into 2 is 0, plus 0.5 into 0 is 0. So, what you have is activation potential to be minus 2. Since it is less than 0, your output is minus 1. Okay. So, this is my architecture, right. So, weight update rule, if you look at, w is equal to w plus eta into y into x, right. Eta is the learning rate. I am assuming the learning rate to be 1. Later on we discuss about what value to select on the learning rate and all this. At this point I am just taking it as a 1. So that initial weight plus 1 into minus 1, right, and the x. This is how the weight changes. Similarly for sample 2, if I just use the activation potential comes out to be 0.75, it is 1. So this is how the weight update happens, and then you get the error. Similarly for sample 3, if I try to do, the output is 4.5 and what we get is y as 1, and I can update the weight, and this is the new weight. Keep on repeating this until you get convergence.
So we will start with the perceptron delta rule. Now let us assume that for all the weights in the perceptron which is given by W. So W is from W1 to Wn, which are all the set of weights for the perceptron. We want to update these set of weights using this. So W is equals to W plus delta W. Now the formula for delta W according to the perceptron delta rule is given by this equation. So delta W is eta times d minus y times xi, where eta is the learning rate, d is the target or the ground truth label, y is the perceptron output, and xi is the corresponding input. Now once we are training the model, when we pass the input to the perceptron and get the output, we can use the delta W rule. Now if the training data is linearly separable, then the delta W would be relatively smaller. So the overall weight update is given by W is equals to W plus eta times d minus y times x. Okay. So what we will do is we will go over an example using the delta rule to update the weights. Okay. So in this example, which is similar to the example used in the Hebbian rule, where we have 3 sets of input S1, input S2, input S3. Now all of these are of dimension 3 cross 1. So essentially when I say S1, S2, S3 in this figure of the perceptron, this set is my input set, which is given by x1, x2, x3. Now for each of these inputs, which is S1, S2, S3, we have a corresponding ground truth label, which is given by D, which is either -1 for the first sample, for the second sample it is 1, and for the last sample it is -1. We use this activation function, which is given by 1 when x is positive and it is -1 when x is negative, which is also highlighted in this diagram in the perceptron. Now x0 and w0 correspond to the bias term, where x0 value is kept as -1. Okay. So we, as seen in the last slide, we initialize the weights randomly, and so w is given by 1, -1, 0, 0.5. The bias is kept as -1. Now whenever we are using the delta rule or even in the Hebbian rule, the steps that we would follow is mainly we would want to compute y, which is the output of this perceptron, which is given as g of x dot w. Once I have calculated the output, we want to calculate the delta w. Once we calculate the delta w, we then want to modify these existing set of weights using this equation. So these are the 3 steps that we will even follow for this example. Okay. So for the first sample, we will compute the output for a given input S1. So this which is given by W, and this is the input X. So W is 1, -1, 0, 0.5. X is given as -1, 1, -2, 0. When we multiply this, we get -2, and once it's passed through the activation function, the value of y results to -1. Since we have calculated y, the second step is to calculate delta w. So delta w is given by this equation, specifically for when using the delta rule. So delta W is eta times d minus y times x. If we put all these values, delta W is 1 into -1 minus of -1 into the input. Since this value becomes 0, the delta W for the first sample is 0. Now following the third step, which is updating the weights, W is equals to W plus delta W, which is essentially using the first randomly initialized set of weights, which is given by 1, -1, 0, 0.5 plus the delta W, which in this case is 0. And hence once we pass the first sample, the update to the weights is essentially no update. So W remains as it is. So it is 1, -1, 0, 0.5. Now we pass the second sample. Now again, as we follow the steps, we first calculate the output to that specific input. Again, it is the activation function of W times x. So when we multiply the recent weights, which is 1, -1, 0 and 0.5, along with the S2 sample given as -1, 0, 1.5 minus 0.5, we get it as, so the output of y after passing it through the activation function is -1. Now again following the same steps, when we want to calculate the overall update delta W, it is given as eta times d minus y times x. Delta W is 1 into 1 minus of -1 into -1, 0, 1.5 minus 0.5, which is the input S2. We get delta W as -2, 0, 3, -1. Now since I have delta W with us, the third step is to update this set of weights. Hence W is equals to W plus delta W, which is given as 1, -1, 0, 0.5, which was the weights, plus the change delta W, which is -2, 0, 3, -1. Hence the new set of weights W is given as -1, -1, 3, -0.5. Okay, this is for the second sample, which is given by S2. Now let us see the third sample. Okay, so again following the same set of steps, the first is to calculate the output. So y is equals to a multiplication of the weights times x. So my recent set of weights is given as -1, -1, 3, -0.5. My S3 sample including the bias term is given as -1, -1, 1, 0.5. Once I multiply this and pass it through the activation function, my y is given as 1. So the output for this particular input S3 with the recent set of weights is 1. Since we have computed the output, let us go to the second step, which is given as, this is given as delta W. Now we have merged the second and third step, which is essentially we are writing the final update, which is given by W. So W is W plus eta times d minus 1 times 1, which is given as -1, -1, 3, -0.5 plus this number, which is eta times d minus 1 times x. X is the current input. Hence W after this addition we get as 1, 1, 1 minus 1.5. Okay. So essentially in this example we have merged the second step, which is to compute delta W and then directly add it to the current set of weights. When I say x, it means the current set of input sample, which is given by S3. Okay. So to summarize, in this particular lecture we have covered the perceptron model, which is essentially a single layer perceptron with different types of activation functions. We also saw different types of Boolean gates. So this is AND gate, OR gate, NOT gate, and we saw how a simple linear separable or a linear decision boundary is good enough to classify the samples as either class 1 or class 2. And lastly, we defined the delta rule, which is used to update the set of weights, and hence we defined the perceptron learning with the specific delta rule. And finally, we computed one example using that specific delta rule. Okay. The next lecture would focus on a deeper dive of again a single neuron and again multiple multi-layer perceptron, however focusing more on the chain rule and the back propagation, and hence defining gradient descent and seeing how it navigates. Okay. Thank you.